Hi, my name is Janani Ravi and welcome to this course on Key Concepts Machine Learning. A little about myself. I have a master's degree in electrical engineering from Stanford and have worked at companies such as Microsoft, Google, and Flipkart. I currently work on my own startup, Lunicorn, a studio for high-quality video content. Machine learning is important because of its wide range of applications and its incredible ability to adapt and provide solutions to complex problems. In this course, you will learn to identify use cases where ML can provide an appropriate solution and recognize common structures in ML-based solutions. First, you'll explore limitations of rule-based approaches and how machine learning mitigates those. You will discover the different types of ML models, such as traditional models and representation models, and see how you can develop the ML mindset to find solutions to meet your use case. Next, you'll explore common ML use cases such as regression, classification, clustering, and dimensionality reduction, and learn the differences between supervised and unsupervised learning. You will also study specialized use cases such as recommendation systems, association rules learning, and reinforcement learning. You will learn to apply ML to complex data using text, images, and speech. Finally, you'll learn how to formulate your use case into one of those problem types so that it can then be solved with a commonly used ML-based approach. When you're finished with this course, you will have the skills and knowledge of the conceptual underpinnings of machine learning needed to recognize use cases for ML and adopt common ML approaches. Hi, and welcome to this course on Key Concepts Machine Learning. In this model, we'll work with basic machine learning concepts, starting by answering the question, what exactly is machine learning? We'll understand how ML algorithms can learn from data. We'll then compare and contrast rule-based learning systems with ML-based learning systems. We'll see that rule-based systems are an example of very simple AI. We'll then move on to discussing traditional ML models and representation ML models. We'll understand what the similarities and differences are, and in the context of representation ML based systems, we'll briefly discuss deep learning and neural network models. You'll find out along the way that traditional software development is very different from model development, and if you're a software engineer transitioning to ML, you need to develop the machine learning mindset. And finally, we'll round this module off by discussing a few examples of AI in the real world. Before we dive into the actual course content, here are some prereqs that you need to have to make the most of your learning. Now, this course requires that you're comfortable programming in Python. Towards the very end, we'll build a simple ML model in Python. However, I do not assume that you have any prior knowledge of machine learning. If you've never worked with Python before, you'll still find this course useful, but at the very end, you won't be able to do the hands-on demos. You might want to watch Python for Data Analysts and Python Beyond the Basics before getting started with this course. Here is what we'll cover in this course. We'll start off by introducing basic machine learning concepts. We'll then move on to identifying the problems that can be solved using ML. We'll then see how we can apply machine learning to complex data such as text and images. And finally, we'll see how we can formulate a simple machine learning solution using the classic ML workflow. Let's dive right in and understand what exactly machine learning is all about and how a machine learning algorithm differs from other software algorithms. A machine learning algorithm is an algorithm that is able to learn from data. Now, you might have encountered other software algorithms before. All algorithms are based on rules and logic, but the output of the algorithm does not change based on the data that you feed in. In the case of ML, the output of your algorithm changes based on the data you've used to train the algorithm. So, how does machine learning work? You're essentially working with a huge maze of data. You have hundreds of thousands, maybe millions of records. What you're looking to do is find patterns in this data, patterns that are interesting, patterns that give you insights about your data. Once the algorithm has found interesting or generalized patterns in the data, You want that algorithm to be able to make intelligent decisions based on the patterns that it has found. Let's look at some examples. Let's say you have a number of emails on a server. These are emails that are coming into your inbox, and you want to figure out which of these emails are spam, that is just some kind of promotion, something you're not interested in, or ham, emails that are important to you. Once your machine learning algorithm has identified the patterns for emails which are spam or ham, your algorithm can then decide whether to move that email to the trash or send it to your inbox. Here is another example of machine learning. Let's say you have a large number of images where every image is represented granularly based on the pixels within the image. Now, you feed all these images into a machine learning algorithm. It's then able to identify edges, colors, shapes, and objects in the image. Based on the patterns found within an image, your algorithm should then be able to tell you this photo, it's of a little girl. Different ML models find patterns of different types and they perform predictions of different types. In order to understand how machine learning algorithms are trained to give us machine learning models, we'll consider a simple example of classification. Classification is an ML technique which involves identifying which category or categories a particular observation belongs to. Here is the example that we'll work with. You're trying to figure out whether whales are fish or mammals, and you want to build a classification model to perform this categorization. If you've studied biology and whales, you know that they are members of the infraorder Cetacea, so they are mammals. But on the other hand, they behave remarkably like fish. They look like fish, they swim like fish, and they party around with other fish in the deep ocean. Now, you want to figure out whether the whale is a fish or a mammal. Before you get into ML, let's build a simple rule based binary classifier. This will accept the input. You'll pass in the information about a whale, and then it will tell you, well, the whale is a mammal. Observe that this is a binary classifier because a whale or any other animal can be classified into only two possible categories, fish or mammal. A rule based classifier doesn't really use any automated algorithms. Instead, you have human experts who understand biology, who may have studied whales, and these humans have drawn up a bunch of rules to allow you to identify the characteristics of a mammal and the characteristics of a fish and classify your input accordingly. Imagine a bunch of rules in the form of if then else statements. These rules are specific to the problem at hand and the data available. So, the rules that these human experts will draw up for rule based classification are not general rules. You can't use this to classify whether a frog is an amphibian or a fish. On the other hand, if you had a machine learning based classifier, that would also be capable of performing this categorization. You'd feed in the features or the characteristics of a whale to such an ML based classifier, and it would give you a result. Now, a machine learning based classifier does not have any inherent knowledge about whales, fish, or any other thing in the world by itself. So, there is no built in knowledge. The knowledge embedded into your classifier comes from the corpus of data that you fed in to train the classifier. Your machine learning model has a number of parameters that it uses to perform this classification. Those parameters have been trained by the corpus of data that you've fed in during the training phase. And this brings us to the two phases of a machine learning model. The first is the training phase, where you feed in a large corpus of data with all of the animals having the right classifications or categorization. The training phase is where the model extracts insights or finds patterns in the data. Once you have a trained model, then comes the prediction phase. This is where your model can be used to classify new instances or make predictions on new instances which it hasn't encountered before. The training of a machine learning model involves feeding a corpus of data into your machine learning algorithm. At every step, the algorithm will output some kind of classification, which is then fed back into the model and used to improve the model's parameters. This feedback function or loss function is used to tweak the model's parameters to give you a more accurate classifier. In the training phase, you have a whole corpus of data with the right labels or classifications. You feed that into some kind of classification algorithm and you can pick the algorithm. There are a whole host of algorithms to choose from. And after the algorithm has been trained, you get your ML based classifier, that is your machine learning model. Once you have a trained model, you feed in the characteristics of the input that you want classified and get a classification. The input that you feed into an ML model is referred to as a feature vector, X variables, or just features. The output that you get from the ML model, the classification or the categorization, is referred to as a label, target, or Y variable. A machine learning model can do amazing things, but it's only as good as the data that you feed in. Let's say you were to tell your classification model the whale moves like a fish and looks like a fish. Your classification model is likely to tell you, oh, the whale is a fish. What's happened here is that you've got your model paying attention to the wrong input. The wrong choice of features was fed into the model, and this led to the prediction of the model being incorrect, where the predicted label was not equal to the actual label. We touched upon this briefly in the previous clip, but in this clip, we'll discuss in detail the difference between rule based and ML based learning. Here is a definition for rule based learning. These systems generate predefined outputs on the basis of previously programmed rules, which are hard coded in the system. The key thing here is to note that the output of such a system is based on rules, and these rules are hard coded. You have to actually go in and change the logic of the program in order to incorporate new information or new rules. The rules in a rule based system typically take the form of an if then expression. If animal gives birth to young, then animal equal to mammal. If animal lays eggs, then animal equal to not a mammal. In our example from the previous clip, we were trying to figure out whether whales were fish or mammals, and we first saw how we could use a rule based classifier for this. Here we have human experts who formulate the rules for this system. The rules created by these experts are very specific to the problem that you're working on and the data that you have to work with. Now, why is studying rule based systems important? As you begin your journey into the world of machine learning and artificial intelligence, you start at the very first step. Rule based systems are a very simple kind of artificial intelligence. This is what we had maybe about 50 years ago. It's important we understand rule based systems before moving on to more complex models. So let's look at the basic components of a rule based system. The first component is a set of facts, and this set holds domain specific knowledge. The facts associated with the classification of animals will be very different as compared with the facts associated with the classification of cars. The next component is a set of rules. These rules make up the rules engine, which is the knowledge base for the system. These rules try to capture everything that experts know about that problem or a domain in order to help you perform classification or make predictions. And finally, we have the third component, which puts everything together. It takes the facts that we know about the problem domain, applies the rules that are part of our knowledge base, and is then capable of deriving conclusions using these two bits of information. Let's look at each of these components in a little more detail, starting with a set of facts. These facts can be held in a database, and these facts record information that is true and that is specific to the problem and domain that you're working in. For example, if you're performing classification of zoo animals, your facts could be of the form birds have feathers, fish breathe using gills, and mammals give birth to young. These are all facts. Next, you have a set of rules, and these rules are in the form of if then conditions. And these if then conditions actually try and capture the relationship between the facts that you have and the conclusions you might make with your data. These rules are also very specific to the problem and domain. Going back to our zoo animal classification, you might have a rule that says if animal has feathers, it's a bird. If animal uses gills to breathe, it's a fish. If animal gives birth to young, it's a mammal. Observe how each of these rules flow directly from the facts that you have. The inference engine takes in the facts, takes in the rules, and then controls the process of deriving conclusions. You can think of the inference engine as extracting or parsing relevant details from the problem instance and then applying the rules in sequence. It then uses these facts and rules to make the final prediction. Let's quickly discuss the characteristics of rule based analysis. Rule based analysis works well when the problem statement that you're dealing with is fairly simple. If you were to try and use rules to identify objects in an image, I don't think you'd succeed very well. Rule based analysis also works well where the rules are straightforward and can easily be expressed in code in the form of if then statements. If you're looking at granular bits of information that take on specific values like has gills, has lungs, facts such as these can be easily codified and expressed in the form of rules. Rule based analysis also works well where the rules are fairly unchanging. Rules don't change very often. If your rules were constantly evolving, that would involve recoding your model at every step, and that's not sustainable. And finally, rule based analysis works well when you have just few problem instances. ML models need a lot of data for training. Rule based systems just need a few examples to help you code up rules. When would you choose ML based analysis? When the problem statement is reasonably complex, like our image classification example that we spoke of earlier. ML based systems also work well where the patterns are more complex than can be captured via if then statements. If it's hard for you to find patterns using visualizations and other exploratory tools, that's when you'd bring in ML. For every kind of prediction, you're looking at a few variables before you make your decision. If the decision variables are many in number and they're sensitive to the data that you feed in and need to change as new information is received, that's the case for ML. ML models will not work well unless you have a large corpus of data available. If you're just working with, say, 100 data points, well, rules are probably sufficient. Let's compare and contrast ML based and rule based models side by side. Starting off with the fact that ML based models tend to be dynamic. The predictions from an ML model will change based on new patterns that it has identified in the data. Rule based systems are static. Rules are formulated upfront and are applied no matter what data you feed into the system. The predictions of an ML based system are probabilistic in nature. Remember, ML models make lots of mistakes. ML models look at the patterns in your data and gives a prediction saying this is the most likely category or this is the most likely value. Rule based systems give you predictions that are deterministic. Rules are clear cut, there is no ambiguity about the rules, and there is no uncertainty about the prediction made by a rule based system. A machine learning based system can be applied to any kind of problem provided you have the right data. You don't need domain experts for that particular problem area. What you need are data practitioners who understand how models work. On the other hand, in order to draw up rules, you need to be an expert in that field. If you're figuring out whether whales are fish or mammals, you need biologists. If you're building a rule based model to figure out whether stocks are going to go up or down, you need a stock market analyst. So, for rule based analysis, experts are vital for formulating the rules, and the experts will be different based on the kind of problem that you're working with. With ML based systems, if you want to update your model to incorporate new information, well, simply update the data that you're using to train the model, update the corpus. In the case of a rule based system, in order to update the model, you need to update the code of the model, that is, the rules that make up the system. It's impossible to get robust, high quality models without a large corpus of training data and high quality training data as that. With rule based systems, you can work with just a few problem instances. You don't need a corpus of training data. ML based systems cannot operate on a single problem instance in isolation. Without training data, there is no ML model. Rule based systems, however, since they operate on rules, can operate on isolated problem instances. With ML based models, there is an explicit training step where you get the ML model to understand the data, to understand patterns in the data. With rule based systems, no such training step is required. Given these differences, when would you choose rule based analysis? Well, where the number of outcomes is small or fixed and the data that you're working with is fairly simple. Also, rule based systems work well where the risks associated with errors are too high. Remember, the output of a rule based system is deterministic. And finally, rule based systems are a good option when you know ML is not feasible. Maybe you don't have the training data. Maybe the rules associated with the problem are fairly straightforward. When would you choose ML based analysis? Well, where you can't code up rules. If you find that the patterns in your data are too complex for if then statements, well, you need ML. ML based analysis also works well where the situations and the data are evolving extremely fast. If the data keeps changing under you, well, your rules won't keep up. If your system has to scale to find a large number of patterns, work on a huge amount of data where the scalable approach is important, make sure you choose ML. Machine learning systems can be further categorized into ML systems based on traditional machine learning and representation machine learning. Let's understand how these are different. Let's go back to our ML based binary classification model. This model is created by feeding a huge corpus of data to a classification algorithm, and that gives us our classifier. This classification algorithm, which learns from data, is a specific kind of algorithm, and there are a whole host of algorithms to choose from. Now, you might go with a support vector machine algorithm, logistic regression, naive Bayes. This choice of algorithm is determined by ML experts. Machine learning experts have a lot of experience with the different algorithms used, and they know which one is the best for your use case. They may even run a bunch of experiments to figure out the best one. In a traditional machine learning model, the corpus of data that you feed in to train your algorithm, the features or the attributes that make up the corpus are determined by experts. Experts need to look at the data that you have and select the right features. Like in the case of our whale classification example, experts have to determine that the right attributes to feed in are the fact that the whale breathes like a mammal and gives birth to young. With traditional machine learning models, they have a fundamental algorithmic structure to solve problems. Each algorithm has its own structure and is different from other algorithms. Whatever algorithm you choose, that is fed in data, and that data trains the algorithm's parameters. Whether the algorithm is logistic regression, whether it's support vector machines, whether it's naive Bayes, the algorithm's parameters will be different based on the algorithm that you've chosen. And the algorithm's parameters are referred to as model parameters. Here are some examples of the algorithmic structures of traditional models. You might build a tree structure to classify instances. This algorithm is the decision tree and is a traditional ML algorithm. You might fit a line on your data or a curve on your data and use that line or curve to make predictions. Examples of these traditional models include linear regression and logistic regression. You can see that the line or the curve structure is a very different algorithmic structure than that of a tree. The third example would be draw a hyperplane in space and use that hyperplane to classify instances. This is what support vector machines do. The design or the algorithmic structure of a hyperplane is different from fitting a line or a curve or setting up a tree. The characteristic feature of traditional ML based systems are you rely on experts to decide what features to pay attention to. So, experts have to select relevant features to train your model, and you rely on experts to determine how those features should be paid attention to. The experts choose the algorithm for your model. Representation ML models, on the other hand, don't really need to be told which features of the data are important or significant. They are able to learn by themselves significant features from the underlying data. The most common and widely used model that belongs to the representation ML category are deep learning models such as neural networks. So remember, the main feature of representation ML based systems are the fact that they figure out by themselves what features to pay attention to and how. So, what exactly is a neural network? Neural networks belong to a category of algorithms that we refer to as deep learning. These are representation ML based systems. These are algorithms that learn what features matter. They are able to extract significant or latent features in the data. ML models classified as deep learning can potentially refer to other kinds of models. Neural networks, however, are the most common class of deep learning algorithms. Neural networks are said to be deep because they can comprise of many layers that adds depth to the model. Neural networks are so called because the basic building blocks that make up a neural network are neurons. Neurons are active learning units. They are responsible for learning from the underlying data. Here is what a neural network looks like. This is a very big picture visualization. A neural network comprises of neurons arranged in layers. Observe that the layers are interconnected. The output of layer 1 feeds into layer 2, which then feeds into layer 3, and so on. The training of the neural network involves feeding in your corpus of data to layer 1, and you will get the prediction from layer n. If you were to take a magnifying glass and look inside these layers, you would find the neuron, the active learning unit that is able to learn from data. A neuron is nothing but a mathematical function applied to its inputs. All neural networks have the same basic structure. What will be different is how the interconnections are designed and how the layers are stacked up one after the other. Unlike with traditional ML, it's not like you have different algorithms. Instead, you have different neural network architectures. Now, what do all of these layers in a neural network do? Each layer is responsible for extracting information from the data fed in as part of your corpus. And each layer extracts a different bit of information. Let's say you're feeding in images in an image classification system. The first layer might look at the pixels in the image. The second layer might put those pixels together to find edges. The third layer might put edges together to find corners. Corners are then viewed as objects. And then finally, you get image recognition or image classification. Let's compare and contrast traditional ML models with deep learning ML models, which we know are representation ML models. With traditional ML models, features used in models are explicitly chosen by data practitioners, data scientists, domain experts. With deep learning models, the feature selection process is not that important because you can just feed in a bunch of data to the model and the model is able to implicitly extract the relevant features. Traditional ML models work with structured data. So you feed in data maybe in the form of rows and columns. The data includes numeric values and probabilities. Deep learning models also work with unstructured data. You can feed in images, movies, and use these as inputs for your predictive models. Traditional ML models solve problems such as classification, regression, clustering, and dimensionality reduction. The same problems can be solved using deep learning models. We'll discuss these problem categories in more detail in the next module. With traditional ML models, there are a wide range of problem specific solution techniques. There are many algorithms under traditional ML models. We discussed a few of these: linear and logistic regressions, decision trees, ensemble models such as random forest. With deep learning models, today neural networks are by far the most common solution technique. In traditional ML, every solution technique has its own characteristic approach, whereas with deep learning ML models, all solution techniques rely on neurons and interconnections. It's the architecture of the neural network that is different. Because traditional ML models are algorithm based, as a user, you have much more insight into the mechanics and the internals of the models. You know why the model gave this particular prediction. Deep learning models tend to be black box models that are hard to question or reverse engineer. You'll build traditional ML models in Python using the scikit-learn framework. For deep learning models, you have TensorFlow, Keras, and PyTorch. Building machine learning models involves a lot of software development, but the machine learning mindset is very different from the software development mindset. Let's talk about how we actually develop traditional software. You have requirements and then you have the final product. So you go from requirements to the product in a sequential or linear fashion. Now let's talk about building and training a machine learning model. The entire process is one of experimentation. You might have to build multiple models, validate your hypothesis, and then figure out which model is the best one. Here are the steps in traditional software development, and this might be familiar to many of you. You first gather requirements to understand what exactly is the problem you're trying to solve. Next, you create a workable design. This might involve the design of the user interface, design of the backend system, the architecture that you're going to use, the tools that you're going to use. Next, you move on to building a prototype, a scaled down version of what you're looking to build, and then you'll use the prototype to iterate. Multiple iterations over the prototype, addition of features in an incremental fashion will give you the final product. And this is the product that you'll ship out to customers. Now, of course, the product might have bugs, and then you'll constantly be fixing bugs, maybe adding new features. When you're looking at building machine learning models, the entire process is iterative and experimental. You'll first set the goal for your analysis. What is it that you're looking to predict? What is it that you're looking to find? You'll then define your hypothesis. Now, hypothesis definition is usually for a statistical model, but for an ML model, your hypothesis might be that using these labeled images, you'll be able to classify these images into cat and dog. The next step for you would be to collect the data. If it's an image classification problem, you need to have a large number of images, hundreds and thousands of images with the right labels. You'll then start the training process of your machine learning model. This can be thought of testing and analyzing your hypothesis. In the case of a statistical model, you'll simply fit the statistical test on your data and see if your hypothesis is proven or disproven. You keep repeating this test and analysis and you reach some kind of conclusion. So you've evaluated your model, you're happy with what you have. And you might then deploy your model to production. Your work doesn't end there. You need to be constantly evaluating your model, even in production, and repeating the entire process. So you refine your hypothesis and repeat. It's not really easy to debug software, but the idea behind it is straightforward. With machine learning models, they encode patterns and make predictions based on patterns. As a human being, it's very hard for us to understand exactly why the model has detected this particular pattern. It's almost impossible for us to interpret why the model does what it does. In short, it's extremely hard to debug mistakes made by models, and that is why artificial intelligence has come under so much fire recently. Models and products may have unexpected interactions with other components of your product, making it even harder to see what exactly is going on. And when you use ML models in your system, it's impossible to devise tests that will test for all possible use cases. Another important characteristic of machine learning models that makes it different from traditional software development is the fact that models degrade in accuracy as soon as they're deployed in the real world. You might train your machine learning model, evaluate it, and be very satisfied that you have a great model for your use case. But a model is at its best just before being deployed to production. If you expect that your machine learning model will behave in production as well as it does in the training and testing phase, well, that's a rookie assumption that will be proved wrong very, very soon. That's because if you build a model and deploy it to production and forget about it, such a model is a static model and these models become less useful over time. A model is only useful if it's constantly retrained on new data. So you need to keep this in mind if you're transitioning from software development to model development. Model development is not exactly the same as software development because a constant stream of new data is needed to keep models working well. Deployed software becomes more robust over time as you fix bugs. But for models, you need to constantly retrain your models on new data so your models adjust for shifting realities in the real world. Releasing a model to production is not the end of a process. In fact, deploying models is just the beginning. There is a lot of work yet to be done. In this clip, we'll discuss a few examples of artificial intelligence that we see around us in the real world. Now, the question is, we use the terms artificial intelligence and machine learning interchangeably. But are they the same or is there a difference? I found that Bernard Marr of Forbes has a very intuitive explanation for the difference between AI and ML. The term artificial intelligence is a much broader concept. The idea that machines can carry out tasks in a way that we would consider smart, that is AI. Voice enabled speakers, those are examples of AI. Driverless cars, example of AI. On the other hand, machine learning is a much narrower concept and is one application of AI. It's a current application of AI based on the idea that we should be able to give machines access to data and let them learn for themselves. So, machine learning and AI, they're the same but yet different. 10, maybe 20 years ago, email inboxes were filled with malware and spam. Email providers today have become extremely good at filtering out spam messages. Spam filters learn from signals such as the words in the message, message metadata, and a bunch of other information. And these spam filters are often personalized based on the user actions that you have performed on specific emails. Spam filters today have eliminated almost all of the spam from our inbox. This is an example of AI. If you look at social media, you'll find that the news articles that you receive in your feed are personalized to you. Personalizing news feed based on what you frequently read, commented on, or liked, that's an example of AI. Social media incorporates other examples of the use of AI. The fact that they're able to recommend people you may know based on friends, interests, or your workplace, that is AI. If you post pictures of you and your friends to a social media site like, say, Facebook, you might find that Facebook recognizes faces based on previously tagged images. It's also capable of recognizing landmarks and locations. All examples of AI. AI is used extensively in banking and personal finance. The fact that you're able to use your mobile phone for check deposits is because they use artificial intelligence to decipher and convert the handwriting on checks to text. Banks also employ AI systems to detect fraudulent transactions. Inputs to this system includes transaction frequency, size, parties involved, a whole host of details. Maps and other traffic based applications use AI powered predictions to help you reduce your commute time. This artificial intelligence system uses anonymized location data from smartphones to analyze traffic patterns in different parts of the city. Apps such as Waze are also able to incorporate user reported incidents, such as accidents that may have occurred, road blockages, construction sites, and so on. All of this information is fed to the maps associated, and this is what helps maps suggest to you the best commute routes. Voice assistants are some of the coolest uses of AI today. Voice to text technology is now accurate enough to allow you to have a basic conversation with your device. Voice technology is now capable of responding to basic actions such as internet searches, setting reminders, setting calendar events. It's also able to perform more complex tasks. Advanced assistants allow you to order items online, answer your questions, play music, hail cabs. And this brings us to the very end of this module on introducing machine learning concepts. Now, we started this module off by understanding what exactly machine learning is all about. We understood that machine learning algorithms are able to learn from data. We then compared and contrasted rule based learning versus ML based learning. And we also discussed when you would choose to go with rule based analysis or ML based analysis. We then understood the difference between traditional ML learning and representation ML learning. We saw that neural networks are the most common examples of representation ML based systems. We then discuss how traditional software development is very different from building and training ML models and how engineers need to develop the machine learning mindset. And finally, we rounded this module off by discussing a few examples of artificial intelligence in the real world. Next up, we'll see how we can identify those problems that can be solved using machine learning techniques. Hi, and welcome to this module on identifying problems solved using machine learning. We'll start this module off by understanding the broad problem categories in ML and how we can choose the right machine learning solution based on the kind of problem that we are working with. We'll then discuss supervised ML techniques and unsupervised ML techniques. You'll find that supervised learning requires labeled training data, whereas with unsupervised learning, the model extracts patterns from the underlying data by itself. We'll then move beyond the basic ML problem categories and discuss a few specialized problems in machine learning, such as recommendation systems, association rules detection, and reinforcement learning. We'll then discuss how we should go about identifying the characteristics of good machine learning problems. When do you know that ML is the right solution for your problem? And finally, once we've identified that a problem needs a machine learning solution, we'll see how we can frame that machine learning solution. Let's get started and let's talk about choosing the right machine learning solution. There are many types of machine learning problems, but as a student of machine learning, these are the first four types that you're likely to encounter. Machine learning used for classification, machine learning for regression, clustering, and dimensionality reduction. All our previous examples to explain what ML is all about included classification examples. So let's talk about classification, which we use to classify input data into categories. When you're identifying the right machine learning solution for your scenario, you'll choose classification when you're looking to predict categories. The output of your model is a class or a category for your problem instance. For example, you might use a binary classification model to figure out whether an email that has come in is spam or ham. Let's say you're dealing with stock market data. Should you buy, sell, or hold on to your stock of Google? The output is one of three categories. This is a classification model. Let's say you're working with image classification. Is the image that you fed in that of a cat, dog, or a mouse? Or if you're working with text data, a classification could be, is this review positive, negative, or neutral sentiment? A second category of ML problems are regression problems. Regression is what you'll use when your output or prediction is a continuous numeric value. Classification models are to predict categories or discrete values at the output. For regression, the output should be a continuous value such as the mileage of a car. Given the characteristics of a car, predict mileage, that's a regression problem. Or given the location and attributes of a home, such as the distance from the city center, the number of rooms in a home, predict its price. That is regression once again. Or for a country, given the country's GDP and other health indicators such as mortality rate, predict the life expectancy of individuals in that country. Another example of regression. Let's then move on to the third category, clustering models. Now, clustering models discover patterns and logical groupings that exist in data. Clustering models are often used for document discovery. Let's say you're investigating a homicide case and you have a bunch of emails that you need to analyze. You might just feed in all of these emails into a clustering model and it will try to find logical patterns in the data. These are personal emails. These are emails where the people are discussing sports. These are emails where something suspicious is going on. Clustering is also used for social media ad targeting, identifying users who belong to the same group or category or have similar interests. Find all users who are interested in sports and push out sports related ads to them. The fourth problem category is dimensionality reduction. Dimensionality reduction looks at the X variables or features that you feed in to extract latent or significant features from data. For example, let's say you're trying to figure out what factors are important in predicting stock movements. There might be 200, 500 factors. Extracting the most significant or latent factors would be dimensionality reduction. Dimensionality reduction is often used to pre-process the data that you feed into other ML models. Performing dimensionality reduction often improves the performance of your ML models, making them more robust. Machine learning models are categorized as supervised learning techniques or unsupervised learning techniques based on how they use the data that you feed into the model. Here is a quote that applies to unsupervised learning. What lies behind us and what lies ahead of us are tiny matters compared to what lives within us. Keep this in mind as we understand the difference. Now, let's go back in time to the first classification problem that we looked at. Whales, are they fish or mammals? We know that whales exhibit the characteristics of both. Now, the way we figured out which ones whales are, was we fed in a large corpus of data correctly classified as fish or mammals to a machine learning algorithm. This model needed this corpus of data with the right labels or classifications. Once we had a trained machine learning model, we could then use it for prediction. We used it to classify new problem instances which it had not encountered before. So, when we trained the ML based classifier, we fed in our algorithm a huge corpus of data. At every step, it output a classification which was then fed back as input to the algorithm to improve the model's parameters. Everything that we've discussed about ML so far refers to supervised machine learning. Here, we know that there is some kind of relationship between the input x variables and the output y variable. Let's represent this relationship using f. So, what we are trying to do is figuring out what is this function f that links the features and the labels. The machine learning algorithm seeks to learn this function. In some cases, as in the case of a simple linear regression model, where your model is just a straight line through your data, we know the structure of that function up front. So, linear regression specifies upfront that the function f is a linear function and of the characteristic form wx plus b, where w is the slope of the line, b is the intercept. However, our machine learning models are obviously much more complex than linear regression. Let's say this function f that links the input x variables with the output target label or y variable is something very complicated. Machine learning algorithms such as neural networks can learn or reverse engineer pretty much any such complicated function given the right training data. If your training data is correct, it exists, it's of a good quality, your neural network can reverse engineer the relationship that exists between the features and the labels. In order to apply supervised learning techniques, you need the labels or Y values associated with each record. Unsupervised learning, on the other hand, learns the patterns that exist in your data without a labeled corpus. So, the machine learning algorithms that you work with can be divided into two broad categories. We have supervised algorithms, where the labels associated with the training data is used to correct the algorithm. The use of labels are what help improve your model's parameters to help it perform prediction. On the other hand, we have unsupervised learning techniques where we do not have a labeled corpus. The model then has to be set up in such a way so that it has the ability to learn structure or patterns in the data without relying on labels. In supervised learning, you have the input variable x and the output variable y. Y is the prediction. The supervised learning technique tries to learn the mapping function y is equal to f of x. It tries to reverse engineer what that f is. The whole idea behind supervised learning is to approximate the mapping function so that if you have a new value of x, then using that mapping function, we can predict y. This reverse engineering is only possible if we have many examples of existing relationships. So, this requires training data to help correct our mapping function approximation. Every supervised learning algorithm learns from the training data that you feed into the algorithm. It then iteratively makes predictions. Each time it sees data, it makes predictions on that data. And for every prediction, the algorithm will check to see whether this prediction was right or wrong. The check will be performed against the actual labels in the dataset. And these checks will be used to correct and adjust the model parameters. Supervised learning techniques require some upfront work by the ML practitioner. We require human intervention to label the records in the training data with the right classes or with the right target values. When you're using unsupervised learning techniques, you only need the input data x. You have no corresponding y for each of your x variables. The algorithm itself is set up in such a way that it's able to model the structure of the underlying data to learn more about the data. Unsupervised algorithms do not have any y values to help correct their predictions or output. These algorithms self discover the patterns and structure that exist in data. As you can see, unsupervised models are pretty self sufficient. Models work on their own with no labeled corpus. But on the other hand, how do you know whether the output of the model is correct? Well, it's quite likely that with unsupervised learning, you may need human intervention to validate the output of the model to see whether the model makes sense. So remember, the main difference between supervised and unsupervised learning is the fact that unsupervised learning does not use labeled training data. Of the four broad ML categories that we looked at earlier, classification and regression models are examples of supervised learning. Clustering and dimensionality reduction models are examples of unsupervised learning. Let's quickly summarize and compare the differences between supervised learning and unsupervised learning. Supervised learning techniques are used when you want to predict outcomes for new instances. You'll use unsupervised learning to get insights from a large data set. With supervised learning, you always know what results to expect. There is a correct result that you can compare against. With unsupervised learning, well, you don't know what to expect. It's the model that will figure out what is interesting. Supervised learning techniques require pre processing to get labeled data. Data doesn't come labeled naturally. However, unsupervised learning can work with unlabeled data, so there is less pre processing involved. Training the model is required for supervised learning techniques, and that can be time consuming. With unsupervised learning, what's time consuming is validating whether the model output is correct. There are a large number of techniques that can be categorized as machine learning. In this clip, we'll go beyond the first few problem categories and look at some specialized problem categories in ML. We'll see how recommendation systems work. Recommendation systems are used to recommend products that users might like, and this is something that you're likely to encounter on an e commerce site. We'll also discuss association rules detection. This is an ML technique that allows you to detect what transactions are likely to occur together. For example, what products are you likely to find in a shopping basket if you have milk in that basket? And finally, we'll discuss reinforcement learning. This is an ML technique where you train an agent to navigate an uncertain environment. This is how robots learn to walk up a hill or in an obstacle course. Let's start off by getting a big picture understanding of how recommendation systems work. At the heart of the system is the recommendation engine. Inputs to the recommendation engine includes products sold on the site and users on the site. The recommendation engine will then try to predict how a particular user rates a product. If the user is likely to give the product a high rating, that product is recommended to the user. There are three possible approaches to recommendation systems. The first is content based recommendations, where you estimate the rating that a user will give a product based on this particular user and this product alone. Collaborative filtering systems use information about other users who belong to the same platform or to the site and other products listed on the site. Or you could have a hybrid approach where you combine both content based filtering as well as collaborative filtering. Let's look at how content based filtering systems work for building recommendation engines. Any successful e commerce site will have a large number of users. These users will have histories. They may have bought products, they may have viewed products. Users' histories and product characteristics are used to figure out whether a user will like a product and then make recommendations. These recommendations may result in more views for that user or more purchases. In content based filtering, items are recommended to users based on the features of the product and the profile of the user. Now, this recommendation is completely independent of other users who may be present in the system. Content based filtering is useful if you have a system with very few users. So it's hard for you to figure out which users are like other users. New items with few ratings where there isn't much of a purchase history associated with that item can be recommended to users using this technique. On the other hand, collaborative filtering techniques employ information about other users to make recommendation decisions. On any e commerce platform, you have certain users who are buying products, and there may be a whole host of other users who like, view, or buy the same products. And collaborative filtering techniques make use of this information. It gets information from an aggregate of users who have liked or rated products. It's not just your preferences that go into the product recommendation that you get, but also the actions of other users who are seen to be like you. Here is a definition for collaborative filtering. Users who agreed in the past will agree in the future. That is, if you and another user like the same product in the past, you are likely to like similar products in the future. So, not only are you like other users, once you like a certain kind of product, you're likely to like similar kinds of items as you did in the past. Collaborative filtering works on the premise that people who buy X will also buy Y. Next, we'll discuss association rules detection, an ML technique which detects transactions that occur together. This is an ML solution that is widely used in the analysis of shopping carts. It's a data mining technique used to identify interesting patterns about what items appear together. For example, beer and diapers appear together very often in shopping baskets. Association rule learning is a rule based machine learning technique. It means that this technique uses ML, that is, feeds off of data to create rules that make up the model. Rules are of the form if X, then Y. If the shopping basket contains beers, it's likely to contain diapers. Or if a shopping basket contains textbooks, it's likely to contain stationery such as pens and pencils. Association rules learning tries to identify strong rules that are supported by probability. If the presence of X means that there is a high probability that Y is also present, that is a strong rule. Strong rules are extremely useful to recommend products, to cross sell or upsell new products to customers. The classic use case for association rules learning is market basket analysis, analyzing what items appear together in a shopping basket. The analysis involves looking at the contents of shopping baskets as a whole to identify which items are sold together. You might see that people who buy diapers also buy beer. Market basket analysis is also used to perform customer segmentation or user segmentation. Find people who like diapers but not beer. Market basket analysis is closely related to recommendation systems, but it focuses on those items that were bought together rather than the user profile and users who are like other users. Next, let's discuss an exciting machine learning technique, reinforcement learning. This is where you train an agent to navigate an uncertain environment. Reinforcement learning centers around decision makers or agents who are operating in an environment that is not known to them. You train those decision makers to take actions to maximize rewards in this uncertain environment. Here are the basic components or processes involved in reinforcement learning. We have the agent. This is the decision maker in an environment. The agent has to be constantly looking around and observing the environment to understand what exactly is going on. Remember, the agent has not seen the environment before. The agent will then take certain actions in the environment, and if those actions happen to be the right ones, the agent will obtain rewards. The whole idea behind reinforcement learning is that the right actions are rewarded and the wrong actions are penalized. And the training process of the agent will essentially cause him to perform more of those actions that are rewarded and perform fewer of those actions which are penalized. The training process in reinforcement learning involves the decision maker exploring the environment and getting feedback from the environment in the form of rewards and penalties. The environment is unknown to this agent and uncertain. For example, if this agent were a walking robot, the robot has no idea whether its next step will cause it to fall down a hole or reach its goal. Falling down a hole will result in a penalty. Moving further towards its goal will get it a reward. The output of a reinforcement learning model is a set of actions rather than a set of predictions. What are the actions the agent needs to take to reach its goal? The algorithm that determines these actions is called the policy of reinforcement learning. Actions are optimized to earn rewards and avoid penalties or punishments. You know you have a problem. Is the machine learning solution the right one for your use case, for your scenario? Well, in this clip, we'll see how you can identify the characteristics of good ML problems. Before you dive into a solution, you need to examine your problem and ask yourself two questions. The first question is, what is this problem that I am trying to solve? The second question is this a good problem for machine learning? Now, it's extremely important that you ask these questions in the right order. Keep in mind that machine learning is just one solution in your toolkit. If you're looking to deploy ML for all problems that you face, well, you're likely to use ML in the wrong situation. Every organization today is obsessed with data collection. But before you jump to collecting the data that you need, understand your problem first. What problem is it that you're trying to solve? I need to recommend useful products to the users of our platform. I need to enable tagging and facial recognition on photos. I need to improve the release processes of my team. I need to automate the solutions that we are now performing manually. You need to know your problem first and then clearly list out possible solution approaches to your problem. Make sure that you kind of zoom out and figure out whether there are other approaches to the problem beyond ML. Think of all of the approaches. Don't jump to using machine learning directly. That may just be the wrong solution. Problems that involve the use of technology may be automation problems or learning problems. You need to distinguish between these. Now, the fact is that machine learning can help automate the processes that you use. For example, let's say you're running an e commerce site where reviews are posted. Machine learning can help identify reviews that are irrelevant or contain terms that you don't want displayed on your platform. ML can help identify these reviews and remove them from display. But it's important to realize that not all automation problems are learning problems. Text analysis, sentiment analysis learns from data. But let's say you were writing a framework to route calls based on button presses to the right team. Well, that's automation, but not learning. So, what are the characteristics of automation problems? When the scenario or your situation is fairly straightforward and you can write out a predefined sequence of steps to automate that process. For example, you may have a process which involves filling out a form and that form is passed along to different teams for approval. You know what steps need to be performed and they are clearly defined. It's quite possible that this is a process that is currently being done in a manual manner. Maybe people are emailing the form to the different teams in order to get approvals. Now, in such situations, there is no actual learning required. The steps that need to be performed are predictable, they are known in advance, and they change very slowly. Let's say you need to add in a new team into the approval loop. That's a predictable, simple change. In such cases, machine learning is not the right tool. Find an automation solution that does not require learning. On the other hand, you might choose machine learning or a learning process where the problem requires learning from data. For example, if you want to be able to recommend products to the customers of your e commerce site, what a particular customer might like may change based on what that customer views, what that customer rates, and what other customers like him or her buy or view. Learning problems are those where you require prediction and not just inference. Inference refers to understanding the relationships in your data. Prediction involves taking those relationships and then making predictions on new unseen data. A machine learning problem needs to be fairly self contained. All of the knowledge needed to solve the problem has to be embedded into the data that you use to train your machine learning model. If there is information outside of the data that you've used for training, well, your model will not be aware of that information or the implications of that information. Use learning techniques in your solution if your model needs relearning when new data comes in. where the new data has to be fed in immediately to the model. Also, a machine learning solution only makes sense if you have the right data to solve the problem. Make sure you figure out whether the data you have is relevant and is the right data. Explore and understand the data, perform exploratory data analysis using visualizations and other processing techniques. You need to ask yourself hard questions about the data. Is the data relevant to the problem? Does the data contain the knowledge that I need to solve what I have here? Also, data is useless if it's not available and accessible. Make sure that the data that you have is in the right format and in the right place and in the right structure that can be fed into your ML model. And finally, are the patterns you find in your data generalizable? Can those patterns be extracted as insights and applied to new unseen data to make predictions? You've identified that your problem requires a learning technique as a solution, and you also have the right data available. So you know that machine learning is the right step. So you go through the entire process of getting a workable machine learning solution. You fit an ML model and then you evaluate it. Make sure that you also have an intuitive understanding of the methodology that the model uses. As we've discussed earlier, debugging ML models is hard, but having an intuitive understanding as to why a model does what it does is useful. Also, remember that ML models are not perfect. They often get things wrong. So, ensure that your problem allows for mistakes. If in your case a mistake can be catastrophic, well, ML is not the right solution for you. If your solution is tolerant of mistakes, ML is the right tool for you. And finally, make sure that the predictions from your model lead to useful decisions, that you actually act on these predictions. Now that you've chosen ML as the right solution to your problem, let's see how you frame a machine learning solution. Always start off with a very clear goal that you state in a simple, straightforward manner. Ask yourself this question: what would you like your model to do? And you should be able to express the answer with a simple statement. For example, I want my model to recommend useful products to shoppers. The statement may be qualitative, but it should capture a real goal and not an indirect goal. Next, think about the best possible outcome. In this case, it could be that shoppers click on and view recommended products. An even better outcome is that shoppers buy recommended products. Your machine learning solution should produce the desired outcome, and this desired outcome is different from the techniques that you use to assess and evaluate your model. The next step is to quantify your success metrics and failure metrics. You might say something like, I want 10% of the shoppers who view recommendations to click through to recommended products, and 2% of the shoppers should buy some of those recommended products. The success and failure metrics are based on the business problem and not the model used. Once again, these are different from the evaluation metrics that you use for your model, such as R square for regression models, accuracy, precision, recall for classification models. The metrics you come up with have to be measurable so that your evaluation is a proper one. So you need to think about how you plan to measure your metrics. When will the metrics be available once your model has been deployed? And can you compare measurements to identify improvements? Ideally, your metrics should allow you to fail fast. If you know that your system isn't working, you want to bail out as soon as possible and not waste more time. Figure out if a solution is a strong no or a weak no. You'll need to take hard calls about how much more time and resources you plan to spend on this system. You have all of your metrics set up. Make sure you choose the right ML solution based on the kind of output that you want. Classification, if you want your instances to be classified into categories. Regression to predict numeric continuous values. Clustering to find patterns and groupings in data. You may choose association rule learning to figure out which items are bought together. And you may choose to build a recommendation system if you want to know if people who like X will also like Y. Next, you need to define and collect the data that you plan to use your model. You need to identify all of the sources of data available. If the required data isn't available, you'll need to make arrangements for ingesting the new data. You need to explore and understand the relationships that exist in the data, and all data may need to be pre processed in order to feed into the model. When you're using ML, you don't have to jump directly to the most complex machine learning model. Start simple, express your problem as simply as possible. You may just start with a subset of attributes that you have available. Also, choose the simplest model possible. The most complex model need not be fit right away. Using a simple model will allow you to prototype your model quickly to see whether ML works at all. The simple model will also establish a baseline for what you expect from the model's predictions. Think of this baseline model as your exploratory tool, and based on how this baseline model has performed, you can make further decisions about the data that you're using and the model that you're using. As you're training your model on data, make sure that your model is actually improving and learning from data. Here is where you ask yourself a bunch of difficult questions. Ask yourself whether you have sufficient data so that the model can extract general patterns. Examine the data and see if there are any inherent biases in the data. Is your data skewed? Do you have a good representation of all of the observations that you see in the real world? This is where you might want to collect more data to mitigate the skewness. Third, ask yourself if your model is generalizing to unseen data. Does your model do very well during training and poorly in prediction? Well, it might be overfitted. You have a good model and you've deployed it to production. Your work is not done. You need to constantly refine and iterate. Evaluate your model against the business objectives and see whether they're being met. Go back and tweak model parameters, improve the design of your model. Experiment with different models, make your model more complex, more simple. That's up to you. Make sure you're always thinking about potential bias in your models. And this brings us to the very end of this module on identifying problems solved using machine learning. We started this module off by understanding the broad problem categories where ML is used, and we saw how we could choose the right machine learning solution based on our scenario. We then discussed supervised and unsupervised learning techniques and saw that unsupervised learning models work without a labeled corpus. We then explored a few specialized problems in machine learning, including recommendation systems, association rules learning, and reinforcement learning. We then discussed the steps involved and the questions that we should be asking ourselves to identify the characteristics of good machine learning problems. Once we know ML is the right choice for our solution, we then saw how we could frame our machine learning solution. In the next module, we'll see how we can apply machine learning techniques to complex data. Hi, and welcome to this module on applying machine learning to complex data. Here in this module, we'll see how we can use ML techniques with three different types of data. First, we'll see how we can use ML with text data. This is what natural language processing is all about. We'll then see how we can use machine learning techniques with image data. We'll talk about convolutional neural networks here. And finally, we'll see how machine learning can be used with speech data, specifically for speech to text conversion. Here are some example use cases of when you would choose to apply ML to text data. Let's say you want to perform the sentiment analysis of reviews on your site. Well, that's ML. Let's say you turn on spam filtering in your inbox. You need to be able to identify the characteristics of spam messages. That's ML as well. Language translation applications, which take a sentence in English and give you a sentence in French. That's ML. Machine learning encompasses all of the natural language processing techniques that you apply on text. Natural language processing is all about using ML to process and analyze large amounts of natural language data, that is, text data. When would you use ML with image data? Image classification is one such example. ML is used in object detection, the ability to identify famous landmarks in pictures. ML is used in facial recognition, the ability to tag your friends in a group photo. Visual search engines, where you feed in an image and get other related images, that's ML as well. And finally, medical imaging and diagnosis. also uses machine learning, the ability to say detect pneumonia or cancer using X ray images. Machine learning techniques have also been extensively applied to speech recognition, identifying speakers and tones. That's an example of ML. Speech to text translation is where ML transcribes audio to text. And finally, personalized voice assistants who answer questions and understand what you have to say. That's ML with speech as well. Let's understand how we would apply machine learning to text data. Let's take an example of a simple classification model. This classifier performs sentiment analysis on data. You feed in the text associated with a review, and it will tell you whether the review was positive, negative, or neutral. Observe that the input to this model is in the form of sentences, that is, it is text input. Now, this makes sense to us intuitively, but there is a problem here. Machine learning models can only process and work with data in the numeric form. They do not work with plain text. This means that if you plan to use text data with an ML model, you need to numerically encode your text so that the text is in the form of numbers. So, how do you do this? Well, consider every bit of text that you're working with as a document, and you then model that document as an ordered sequence of words. So, here is my document, my review. I'm going to first tokenize the document into individual words. So, I've extracted all of the unique words in this document. Once I have the individual words in a document, I represent each word as a number. So you need to numerically encode every word in your input document. So going from x0, x1 all the way to xn, you now have numeric values for every individual word in this document. With these numeric values, you can represent each word as numeric data and put these together into a tensor. A tensor is nothing but an array. The question now is, how best can words be represented as numeric data? What is the number associated with each word? And there are different techniques that you can use to achieve this. The first of these is one hot encoding. You then have frequency based encodings, and you also have prediction based encodings. All of these are techniques to represent text in numeric form. Let's start off by looking at one hot encoding first. When you're using text to train an ML model, you won't have a single document, you'll have an entire corpus. So imagine that one movie review is a single document in an entire corpus of movie reviews. Now, tokenize every review in the corpus so that you get all of the words used in the text. What you'll get now is a set of all of the unique words that appear in your reviews. One hot encoding involves expressing each review as a tuple of elements which are either 1 indicating the presence of a word or 0 indicating the absence of a word. The review with just the word amazing will have 1 for the word amazing and 0 elsewhere. The review that says worst movie ever will have 1 corresponding to each of these words, 0 elsewhere. The review that says 2 thumbs up will have 1 against each of these words, 0 elsewhere. Thus, every review is expressed as a vector with 1, 0 values. 1 indicates the presence of a word, 0 the absence of a word in a review. Observe that with one hot encoding, you've lost the original order of the words in the review. You've also lost semantic information. One hot encoding does not capture any semantic information or the relationships that exist between words. Next, let's look at frequency-based encoding techniques. Now, there are several techniques that fall in this category, such as count vector encodings, TF-IDF, that is term frequency, inverse document frequency, and co-occurrence matrices. We won't discuss all of these in this particular clip. Let's look at TF-IDF because this is a commonly used technique. The TF-IDF encoding for a word tries to capture how often that word occurs in a document as well as across the entire corpus. Remember, the idea is to numerically encode words so that these numeric values can be aggregated into a tensor or an array. Now, TF-IDF represents each word with the product of two terms, the term frequency and the inverse document frequency for that word. The term frequency is a measure of how frequently the word I occurs in document J. Document J, is a single review in our corpus. The inverse document frequency measures how infrequently the word I occurs across the entire corpus of documents, that is, our entire set of reviews. The term frequency or TF score for a word will be higher if that word occurs very often in a single document. Let's say the word awesome occurs 5 times in a review. Well, the term frequency that is going to be high. On the other hand, the inverse document frequency of a word will be low if that word occurs frequently in the corpus, because then the algorithm thinks that this is a common word such as a, an, the, this, and so on. Words can be represented using prediction based encodings as well, and these are often referred to as word embeddings. Word embeddings are numerical representations of text which capture the meanings of words and also semantic relationships that exist between words in the same sentence or the same document. This is the basic principle that underlies word embeddings. Words of a feather flock together. The whole idea here is if certain words appear in sentences together, that means there exists a semantic relationship between those words. And when you generate numeric values for those words, that should include the information in the sentence. Generating embeddings for words require the use of ML. This machine learning algorithm has to be trained on a large corpus of text data to identify which words appear together. Once you have a trained model, you'll feed in a word like London and get a numeric representation for that word. This ML based model works in such a way that words that are similar to one another will have similar embeddings. So let's say this is the embedding for London. Cities which are similar to London, such as New York and Paris, will be numerically close to the word London. Thus, every word can be numerically represented with low dimensionality. Now, this ML model requires a large corpus of text data on which it needs to be trained, such as all of Wikipedia. This ML model is typically an unsupervised learning algorithm which works in the absence of a labeled corpus. Now, word embeddings are like magic because they capture meaning. The relationship between the embedding for queen and king will be similar to the relationship between woman and man. Or the relationship for the embeddings between the cities Paris and France will be like the relationship between London and England, capitals and countries. There is dramatic dimensionality reduction representing each word, meaning and relationships are captured. Before you encode words in numeric form, there is a bunch of pre processing that you may need to perform on your text data. All of these pre processing techniques are part of the natural language processing toolkit. Pre processing techniques include stop word removal, frequency filtering, stemming, and lemmatization. Stop word removal gets rid of irrelevant words. It's based on the premise that the more common a word is, the less information is contained within that word. And extremely common words such as an, this, the, etc., contain no information at all. Stop word removal involves filtering out these irrelevant or non information containing words as a pre processing step before you apply other techniques on your text data. Stop word removal tends to be language specific, and the stop words are usually taken from a user specified repository. So, it's a dictionary of words which are considered stop words. So, there is no universal definition of what exactly a stop word is. In order to make this filtering more objective, it might be better to remove irrelevant words based on their frequency. If a word occurs very often in the corpus, you'll basically say that word contains no information and then you'll eliminate that word from your text. This removes the need for externally specified stop words and can apply to all languages. You might specify a rule such as this one: remove all words that occur more than 1,000 times across the corpus. You can also filter out low frequency words. Remove words that occur fewer than 3 times across the corpus because that word is likely to be a misspelling. Stemming is a heuristic process applied on text to chop suffixes of words. For example, let's say you have the words eating, eaten, and eat. They all kind of represent the same thing. They are the same semantically. All of these will be stemmed to just eat. Now, the idea behind stemming is conceptually similar to lemmatization, which we'll discuss next, but it's more crude because this just chops off suffixes. Stemming allows different forms of the words which mean the same thing to be grouped together as the same word. Now, stemming need not create a stem that is identical to the morphological root of the word. In fact, the stem that is generated from the words need not be a real word by itself. It can just be some kind of prefix that appears across many words. Another technique applied to your input text may be lemmatization. Lemmatization is very similar to stemming. The purpose is the same. The idea behind stemming as well as lemmatization is to group related forms of words together. So basically, words which have different forms but mean the same thing should be a single word. Lemmatization reduces the word to its base form, and this base form is referred to as a lemma. Lemmatization is a much more complex and nuanced technique than stemming. It's more involved than merely chopping off suffixes. Lemmatization involves use of a dictionary or a lexicon for that particular language, as well as parts of speech tagging on your sentences. For example, in English, words such as am, are, is will all be lemmatized to its base form be. In this clip, we'll discuss what is involved in applying machine learning to image data. Now, we worked with image recognition algorithms. If you've not built them, you've at least used them. That's what is used while tagging your friends on Facebook or some other social media site. Images are not numeric in nature, but the pixels of images can be represented in numeric form. So, for these ML techniques, images are represented as pixels. They are then fed in through a neural network model that can identify edges, colors, and shapes within the image. And then the neural network might say, hey, this is a photo of a horse. Remember, machine learning models, whether they are neural networks or traditional machine learning models, can only work with numeric data. An image has to be represented as a matrix. A matrix is a tabular format with rows and columns, and every cell in this matrix contains a numeric value. So each cell in this matrix represents one pixel in the underlying image. The value used to represent a pixel depends on the type of image that you're working with, whether it's a color image or a grayscale image. In the case of a color image, every pixel is represented using three values, three separate numbers. Color images are also known as RGB images, where RGB stands for red, green, and blue. So, a single pixel in a color image is represented using three separate values, one for R, one for G, and one for B. And these values are numbers in the range 0 to 255. A red pixel will be represented using three values, 255 for red, 0 for green, 0 for blue. A green pixel will be represented using three values, 0 for red, 255 for green, and 0 for blue. And a blue image will be represented using three values once again, 0 for red, 0 for green, and 255 for blue. Three values to represent colors. These three values correspond to the three channels of an image. Rather than working with RGB values in the range 0 to 255, these numbers are often scaled to be in the 0 1 range, where 1 represents 255, 0 represents 0. That's because images are usually fed into neural networks, and neural networks perform better with very small values. What if you're working with an image that is not a color image? Grayscale images are also represented as matrices. So we have a grid where every value in the grid represents a pixel. Each pixel represents only the intensity value for that pixel. So grayscale images have just one value for each pixel, the intensity. A single pixel in a grayscale image will have just one number. For example, 0.5. That is the intensity of that pixel. One value to represent intensity. Grayscale images are referred to as single channel images. A matrix of pixel values can be used to represent both grayscale images as well as color images, single channel as well as multi channel images. The matrix used to represent images is a three-dimensional matrix. The first two dimensions in this matrix correspond to the height of the image and the width of the image. Now, the number of channels specifies the number of elements in the third dimension of an image matrix. Consider a grayscale and color image of the same size, 6 pixels by 6 pixels. 6 by 6, those are the first two dimensions. Observe that for the single channel image, that is the grayscale image, the third dimension has just one element. This is the single value that represents the pixel intensity. For the multi channel image, that is the color image, the third dimension has three elements. These are the three elements that represent the RGB values of a pixel. Images are usually fed to deep learning models such as neural networks. Deep learning frameworks used to build neural networks do not normally deal with a single image at a time. Instead, they deal with a list or a batch of images represented in a single four-dimensional matrix. In order to be able to represent a batch of images as a four-dimensional matrix, it's important that all of the images be of the same size. So, as a pre-processing step to feeding images to a neural network, you generally resize the images so they're all the same size. Here is a four-dimensional matrix to represent a batch of 10 images. The last dimension refers to the number of channels. Now, this batch comprises of color images, and that's why the last dimension is 3. The middle two dimensions of this 4D matrix represent the height and width of every image in the list. Keep in mind that all of the images in this batch will be of the same size. Here they're all 6 by 6 images. And finally, the first dimension here refers to the number of images in this batch, and that is 10. Neural networks that work with images are referred to as convolutional neural networks. Now, this is a beginner course, so we won't talk about how convolutional neural networks or CNNs work. However, we'll understand the high level intuition behind CNNs. Convolutional neural networks are modeled on how your brain perceives images. Now, all of the neurons that reside in your eye don't see the entire image. So, when you're looking at an image, such as this one of my dog here, the neurons in your eye will not take in the image in its entirety. In fact, every neuron in your eye will focus on a portion of this image, and that is referred to as the local receptive field of that neuron. There are millions of neurons in your eye connected directly to the brain, and each neuron only looks at what is in its local receptive field. So each neuron reacts only to visual stimuli located in its local receptive field. The local receptive fields of all of the neurons put together will take in the image as a whole. Some neurons view the image directly, other neurons react to more complex patterns that are combinations of lower level patterns. So, other neurons get their input from the neurons that are directly stimulated by the image. And if you think about it, this is exactly how neural networks work. This is a classic neural network problem. The neurons in the initial layers look at granular details, then neurons in other layers aggregate those details to find more complex information in the image. Convolutional neural networks are made up of two kinds of layers. Convolution layers, these are the layers where the neurons react to visual stimuli in the local receptive field. You can think of convolution layers as looking at only small portions of the input image. The output of the convolution layers are often fed into pooling layers. Pooling layers subsample the input, so they take very dense input, perform some kind of sampling to get a little less dense output. Convolutional layers in a CNN is essentially a sliding window function which is applied to an image, and it extracts feature maps from the underlying image. These feature maps represent the granular features of an image. These convolutional feature maps can be used to identify edges in the image, horizontal or vertical or diagonal edges, can be used to identify corners, identify changes in intensity, and so on. Pooling layers, on the other hand, perform a different kind of function. They subsample inputs to reduce the spatial representation of the image. Remember, images are very dense data. With the help of subsampling, pooling layers reduce the density of the input image, and this is what also extracts information in the form of aggregates. These two layers form the fundamental building blocks of convolutional neural networks. A CNN comprises of alternating convolutional and pooling layers. So we have a bunch of convolutional layers and then a pooling layer and another set of convolutional layers and so on. These CNN layers then feed their output to other output layers, which then emit probabilities which are used to classify images. In this clip, we'll discuss how machine learning techniques can be applied to speech data. Now, the example that we'll work with is that of audio speech recognition or ASR. The input to this audio speech recognition model is an audio wave. These form the features of your data. The output of this ASR model will be a transcript. This is essentially the text that corresponds to your input audio wave. This is the label associated with your input features. We know that machine learning models can only process numeric data, but audio data consists of sounds and noises, and human speech is a special case of audio data. This means that you have to pre process audio waves before you can convert it to a form that can be fed into an ML model. Let's look at the pre processing steps one at a time, starting with loading in audio files. These audio files might be MP3 files, they might be WAV files. These are the files that form your input. They contain speech in a spoken format. Now, these audio files are actually read in as an array of numeric values. Each numeric value used to represent audio is a measure of the intensity of sound at a particular moment in time. The number of numeric values used to represent your audio data is determined by something known as the sampling rate. So, a sampling rate of 44.1 kilohertz will result in an array of 44,100 numbers for 1 second of audio. You may then want to resample your audio and convert your sound to either the mono format or the stereo format. Audio sounds can have either one or two channels. So, monophonic sound or mono contains a single channel of audio. Stereophonic sounds or stereo contains two channels. The dimensions of the array read in from the audio file will differ based on type of sound, either mono or stereo. Your machine learning model will work with audio samples of uniform dimensions. So, this might require a conversion. Now, audio data contains a lot of variations. Your audio files may have been sampled at different rates. They may have a different number of channels. Some may be mono, some may be stereo. It's also possible that all of your audio files for speech to text conversion are of different durations or different lengths. Now, deep learning models work with data of uniform sizes. So, you might need to do a bunch of data cleaning to standardize your audio dimensions. This data cleaning might be any number of steps. You might want to resample with the same sampling rate across all audio files to create fixed length input. You might want to convert all of the audio to have the same number of channels, either mono or stereo. You might also use padding or truncation on the input files to convert all files to be the same duration. In order for your deep learning model to better understand the audio data, you could choose to apply some audio augmentation techniques. The objective of audio augmentation is to add some variety to your input to help your model learn better from the data and generalize better from the data. Some augmentation techniques include time shifting the audio either left or right, changing the pitch of the audio, or tweaking the speed of the audio. These techniques are optional, but they may help build more robust models. The next step in the pre-processing is to convert the audio to be represented in terms of MEL spectrograms. First, let's understand what exactly a spectrogram is. Now, audio signals are in the time domain when you convert them to the frequency domain that gives us a spectrum. Audio waves are examples of non periodic signals. It's not that the same pattern repeats over time. For non periodic signals, these frequencies vary over time. You can then apply a transformation using overlapping windows on this spectrum. So the window will operate on different segments of a signal, and the result will be something known as a spectrogram. A spectrogram is a visual representation of a spectrum of frequencies as the frequencies vary over time. A Mel spectrogram is essentially a spectrogram where the frequencies are converted to another scale known as the Mel scale. So, why do we need the spectrogram in a Mel scale? Well, human beings do not perceive frequencies on a linear scale. There are a certain range of frequencies to which we are much more sensitive. We are better at detecting differences in lower frequencies than higher frequencies. If we had to distinguish between a sound at frequency 400 Hz and 500 Hz, those sounds would sound very different to our ear. But on the other hand, if we were to detect the difference between frequencies at 14,000 Hz and 14,100 Hz, we would be unable to do so, even though the difference in both cases is the same, 100 Hz. The Mel scale is a unit of pitch such that equal distances in pitch sound equally distant to the listener, to a human listener. And this is why the Mel spectrogram is used, which represents the spectrogram in the Mel scale. Once we have the Mel spectrogram, you might optionally want to perform some spectrogram augmentation. These augmentation techniques include frequency and time masking. This randomly masks out either vertical or horizontal bands of information from the spectrogram. Time masking masks out vertical bands, frequency masking masks out horizontal bands. The MEL spectrogram then may be converted to something known as the MFCC. This stands for the MEL frequency cepstral coefficients, and it's a compressed representation of the MEL spectrogram. Converting to MFCC extracts only the essential frequency coefficients corresponding to human frequency ranges. And using MFCCs as input to your model may help in better recognition of human speech. Once you've pre-processed your data and got it in the right format, there are several deep learning architectures you can use for audio sound recognition. Baidu's deep speech model is a combination of a convolutional neural network plus a recurrent neural network which is used to demarcate each character of the words in speech. Google has its own model known as the Listen, Attend, Spell or the LAS model. This is a recurrent neural network that treats each slice of the spectrogram as one element in a sequence. And this brings us to the very end of this module on applying machine learning to complex data. We started off by seeing how we could apply machine learning techniques to text data, specifically how we can convert text to numeric form. We then focused on applying machine learning techniques to image data. We saw how images could be represented as matrices and understood the intuition behind convolutional neural networks. And finally, we rounded this module off by seeing how we could apply machine learning to speech data. In the next module, we'll get hands on and we'll see how we can formulate a simple machine learning solution. Hi, and welcome to this module on formulating a simple machine learning solution. In this module, we'll finally get hands on and we'll build a very simple machine learning model, a regression model. But before that, we'll quickly understand what exactly linear regression is all about. We'll then identify the key steps in the machine learning workflow. We'll then switch over to Jupyter Notebooks running Anaconda, Python, and we'll see how we can explore and pre-process the data to set up our regression model. And finally, we'll build a very simple machine learning model to perform simple linear regression using the scikit-learn library. We'll use a single predictor variable to predict the target. Let's look at a quick overview of how linear regression works. Let's say you know that X causes Y. Here, the cause is the independent variable and the effect is termed as the dependent variable. Another term that you can use for the cause is the explanatory variable. If you have X causes Y, you can maybe plot the data points in your data on a coordinate plane such as this one. Here, for the sake of simplicity, we assume just one feature or independent variable x. This is plotted along the x-axis. The target value y is plotted along the y-axis. Linear regression involves finding the best fit line on this data. How do you know which line is the best fit? Let's compare two lines we have here, line 1 and line 2. Now we have all of the original data points. Let's drop vertical lines from each of the original data points to the lines 1 and 2. We can observe something about these projected lines. Their lengths are different. The best fit line is the one where the sum of the squares of the lengths of these dotted lines is the minimum. These dotted lines are referred to as errors, and the best fit line is found by minimizing the least square error of your data. This technique of finding the best fit regression line is referred to as ordinary least square regression. And the best fit line found in this manner is referred to as your linear model. Now, the residuals of a regression are the difference between the actual and the fitted values of the dependent variable. Here, the actual value of the dependent variable is, say, yi. The projected value of the dependent variable on the regression line is yi prime. This difference between the actual and projected values are referred to as the residuals of a regression. Another way to express the best fit regression line is that line which minimizes the variances of the residuals. This is also referred to as mean square error regression. Simple regression is regression analysis when we have one independent variable and one dependent variable. If you have multiple independent variables, that's multiple regression. And the same concept of finding the best fit line can be applied to multiple regression as well. Regression models are evaluated using a metric known as R square. R square is computed by this formula ESS divided by TSS. ESS here is the explained sum of squares and TSS is the total sum of squares. ESS is a measure of the variance of the fitted values on our regression line. TSS is a measure of the variance of the actual values in our data set. Thus, R square represents the percentage of total variance explained by the regression. Higher the R square, better the quality of the regression. R square, of course, cannot exceed 100%. When you perform multiple regression, not all of the features might be relevant. The metric used to evaluate a multiple regression model is the adjusted R square, which is essentially the R square which is multiplied by a penalty for adding irrelevant variables to the regression analysis. If you're building and deploying a machine learning model to production, there are a sequence of steps that you need to follow, and those steps are incorporated into the classic machine learning workflow. Here is what the ML workflow looks like. There are lots of steps here, but we'll walk through this one by one. Now, the first step is for you to consider what data you have to work with. The data that you have will be in the raw format and may not be suitable to feed into machine learning models. For example, if your data is image data or text data, you'll have to further pre-process that data. The first step is to have the data available to you in a database or the file system where you can access the data. So you load and store the data and then you clean and pre-process the data. Cleaning the data might involve exploratory data analysis and other techniques to find missing values and outliers in your data. Your data may also need to be processed further. If it's text data, it may need to be converted to a numeric form. Once you have your data in the right format, that's when you choose an algorithm to fit on your data. Should you use support vector machines or should you use decision trees or logistic regression? This is where you make that choice. You then feed the data that you have into the algorithm that you've chosen. This is the training phase, which tries to determine the model's parameters. Once your algorithm has completed the training process, what you have is a machine learning model. Once you have the model, you need to check to see whether the model is a good one. You select a validation method for your model and you choose your evaluation metrics. Apply the validation method and examine the fit of the model. So, this is where you generate a score for the model, such as the R square score for a regression model. After you've evaluated your model, you might find that you're not satisfied with the performance of this model. Remember, machine learning is an iterative experimental process. If you're not satisfied, you might need to update your model. Maybe you need to tweak the design parameters of your algorithm. Maybe you need to choose a different algorithm. Maybe you need more training data. Maybe you need to train for longer. Now, this cycle continues till you're finally satisfied with the model. So, iterate over this series of steps till the model has been finalized. And when you're finally satisfied with the model, you can deploy this model to production and use it for predictions. Deploying a machine learning model is not the end of the process. Once your model is in production, it will get stale unless it's retrained constantly using new data. And these are the basic steps in any machine learning workflow. In this demo, we'll build a very simple model to perform linear regression. Linear regression will fit a straight line on our data, and that straight line will be our predictive model. And here we'll perform simple linear regression. Linear regression with just a single predictor variable. We'll write our code using Jupyter notebooks. I have my notebook server running and I'm working with the Anaconda distribution of Python, which comes with a variety of libraries for data science already installed. Here is my current working directory. I have a datasets subfolder under here which contains the datasets that we'll work with. Salary.csv file, that is the dataset that we'll be using for regression. Let's go back to our current working directory and create a new notebook. Observe that I'm running Python 3. This code should work on any version of Python 3.6 and above. Let's rename our notebook to have a meaningful name. Simple linear regression is what I have called it. We are now ready to get started coding. First, let's set up the import statements for the Python libraries that we'll use. We'll use NumPy and Pandas to work with data. The linear regression model from sklearn.linear model, that's what we'll use to perform ML. We'll use model selection test train split to split our data into training data and test data, matplotlib and seaborn for visualization. All of these libraries are part of the Anaconda distribution of Python, or you can get them with a simple pip install. Let's read in the salary data. The salary data set is available freely here at kaggle.com. It's an extremely simple data set. If you look at a sample of records, you'll see that we have just two columns. The first column gives us the number of years of experience for an individual, and the second column, the salary, that is annual salary for an individual. Observe that there are certain records with missing fields in the years of experience column. Those missing fields are represented using nans or not a number. Now, this is a very simple data set. It's also a small data set. If you take a look at the shape of the data frame, you'll see that we have just 39 records, and each record we know has two columns. You can confirm the presence of missing values in your data by invoking the info function. Observe that there are only 33 non-null values in the years of experience field and 39 non-null values in the salary column. The describe function on a pandas data frame will give you a quick statistical overview of the data that you're working with. Summary statistics such as count, mean, standard deviation, median, and so on. The average years of experience an individual has in this dataset is about 6.28, and the average salary is about $209,000. The standard deviation for salary is about $493,000. The standard deviation for salary is $493,000 roughly, which seems to indicate that there are many outlier values in the salary column. Another indicator that our data set contains outlier values for salary is a measure of skewness in the salary data. If you notice, the skew for years of experience is 0.44, so very close to zero. This seems to indicate that asymmetrical values far from the mean are not very likely in years of experience. But the skew for salary is 5, that is far away from zero. This is another indication that there are outliers in the salary data. Now I'm curious to see how my data is distributed. So I'm going to plot a histogram of the years of experience field. I'll also plot a KDE curve, which is essentially a smooth curve representing the same data as a histogram. This histogram shows me that there is no clear shape to the distribution, but you can see that there are also no extreme values. The years of experience range from about 0 to 13. Now let's take a look at the salary data using a histogram as well to see how salary data is distributed. And here immediately you can identify the presence of outliers. You can see that most of the salary information is between 0 and $100,000. But there are individuals in this data set who have a salary of 1 million, 3 million. All of these are outliers with huge salaries, and this is what is affecting the mean and the standard deviation. Let's view the box plot representation of the years of experience. This will give us a quick overview of the summary statistics for this column. The center line of the box plot, the median years of experience is about 5 years. The box represents the interquartile range. The value at the 75th percentile, that's the upper edge of the box. The value at the 25th percentile is the lower edge of the box. You can see that the interquartile range goes from about 3 years to about 9.5 years. Let's look at a box plot for the salary information as well. And immediately, what should jump out at you is the presence of outliers. There are definitely individuals with salaries ranging from about 500,000 to 3 million. These are the outliers in our data set. We can't work with this data directly for regression analysis. We'll need to do a little bit of pre-processing on this data to take care of missing values in fields as well as outlier information. So let's now compute the interquartile range. Here is the data at the 25th percentile. 3.2 years for years of experience and roughly $57,000 for salary. Next, let's get the data point at the 75th percentile, that is quartile 3. Now we'll get this for both years of experience and salary, 9.5 years for years of experience and $122,000 roughly for salary. I'm now going to use this quantile information as well as the interquartile range to help me identify outliers in my data. So compute the interquartile range Q3 minus Q1. You can see that it's 6.3 for years of experience and roughly $65,000 for salary. I'm going to consider those data points as outliers if I find that their salary is 1.5 times the interquartile range below quartile 1, below the 25th percentile, or 1.5 times the interquartile range above Q3, the 75th percentile. Data points above and below the whiskers in the box plot are outliers. That is my definition of an outlier, and this is what I think makes sense for this dataset. This is exactly the computation that I have performed. In order to train my ML model, I'll only include those salary records that fall within the box plot's whiskers. I'll get rid of all of those records where the salary is 1.5 times the interquartile range above Q3 or below Q1. Here I've identified the outliers in my data. Here are 4 records where the salary values are very high. Those are what I consider outliers, 500,000 to about 3 million. In order to remove these records from my data, all of the outliers, I'm going to use the negation sign. This will essentially filter out the outlier records, and I'll be left with records that I consider make sense to train my ML model. So my salary data now has 35 records. I've gotten rid of 4 records with outlier salary values. If you were to now look at a box plot representation of the salary data available in our dataset, you'll find that all of the outliers have been removed. The median salary is about 80,000. Now, this is the data that we'll use to train our simple regression model. Our data pre-processing isn't complete. We still have missing values in our data that we have to deal with. Is null sum tells us that we have 6 records with missing values in the years of experience column. Now we have a rather small data set, and I'm not comfortable dropping any more records because we'll just have fewer records to work with. What I will do is compute the mean value for years of experience and we'll use this mean value to fill in the missing fields in this column. The fill NA function in a pandas data frame does exactly this. We'll fill all of the missing values in the years experience column with the average value of that column, and we'll do this in place. Now, if you compute is null sum to see how many missing values are in your data, you should find the values 0 for both years of experience as well as salary. So we've filled in the missing values in years of experience using the average value for that column. And this is a legitimate technique. After having performed all of this processing, let's take a quick look at the summary statistics in our data using the describe function. You can see that the average value for years of experience hasn't changed because we filled in with the average, that's 6.5 years. The average salary for our current set of records is about $84,000. The mean has fallen because we've eliminated the outliers in our data. And finally, just before performing simple regression, let's visualize the relationship that exists between years of experience and salary using a scatter plot. And in this very simple data set, you'll find that there is indeed a straight line relationship that exists between years of experience and salary. More years of experience you have, higher your salary. And you can see this by drawing a line through the records. Having explored, visualized, and pre-processed our data, we are now ready to fit a simple regression model. Let's first split our data into predictor and target. The X variable is the years of experience. This is what we'll use to predict the salary of an individual. The Y variable or the target is the salary. Next, we'll split our data into training data and test data. We use the train test split function in scikit-learn for this. This shuffles our data so our model doesn't pick up inadvertent patterns and then splits our data. Our test size is 0.3, which means that we'll use 30% of the existing data to evaluate our model. The remaining 70% will be used to train our ML model. Let's take a look at the number of records we're working with. Our training data contains 24 records, test data 11 records. The training and the test data are both vectors with a single dimension. The training data has 24 elements, test data 11 elements. Let's take a look at the Y variables or the target. Once again, 24 and 11 elements respectively. The linear regression model in scikit-learn, which we'll be using to train our simple regression model, expects the input training data to be in 2 dimensions. So we'll need to reshape the original data. I first convert the training data to a NumPy array, then we invoke reshape -1, 1. This will ensure that the second dimension has just one element and the first dimension will be the length of the original vector. I then perform the same reshape operation on the target variables in the training data. Observe that the shape of the training data now is in the form of a multi-dimensional array. 24 elements in the first dimension, one element in the second dimension. The single element represents the single X predictor or the single Y variable, the target. We need to perform the same set of reshape operations on the test data as well. The representation of the test should be the same as that of the training data. So here are the reshape operations on the X data and the Y variables, and you can see that the test data is also in the form of a multi-dimensional array. We are now ready to train our ML model. Let's instantiate the linear regression estimator object and use this object to call fit on the training data. The fit method in scikit-learn starts the training process. This will fit a simple regression model on our single predictor and target value. Now that we have a trained model, let's take a look at the coefficients of this model. There is a single coefficient corresponding to our years of experience predictor. The fact that this coefficient is positive indicates that there is a positive relationship between the years of experience and the salary of an individual. Next, let's look at the intercept that this model founds. The intercept is along the y-axis and we have a positive value for the intercept as well. Now that we have a model, we can use it for prediction. Let's invoke the predict function on the test data. Observe we pass in only the x variables, we don't specify the y. We get the predicted y values from the model and here is a sample of the results. But how do these predictions match up against the actual data? We can score our regression model. Let's first score our regression model on the training data. This gives us the R square score of our model on the training data, and you can see that it's 0.87 or 87%. 87% of the underlying variance in our data points was captured by our linear model. The real test is, of course, the R square score on the test data. This will tell us how well our model performed in prediction using new unseen data points. And the R square on the test data is almost 91%, higher than the R square on the training data. This is clearly a very good, robust model. Let's look at the actual linear model that was fit on the training data points. I'm going to plot a scatter plot of the training data. These points will be in orange, and then I'm going to fit a line that represents a regression model. And you can see from this result here that the linear model is a great fit on the training data. But how does our linear model fit on the test data? Let's plot the test points in the form of a scatter plot in green, and then let's fit the regression model on the test data to this scatter plot. And you can see that our regression line fits our test data fairly well. And this demo brings us to the very end of this module on formulating a machine learning solution. We started this module off with a quick overview of linear regression. We understood what it means to fit a linear regression model on data, and we saw how regression models can be evaluated using the R square metric. We then identified the key steps in the machine learning workflow, starting with the raw data, and we ended with a deployed model. We then got hands on with a very simple dataset, the salary prediction dataset. We explored and pre processed the data to set up the regression model. And finally, at the very end, we performed simple linear regression with a single predictor variable using the scikit-learn library. And with this, we come to the very end of this course, Key Concepts Machine Learning. Now, if you're interested in studying further, here are some other courses that you might find interesting: Foundations of Statistics and Probability for Machine Learning, and Approaches to Data Enabled Decision Making. Well, it's time for me to say goodbye. That's it from me here today. I hope you enjoyed this course. Thank you for listening.